5. We couldn't get those to work. I did those a different way and it counted it right. We got it right. So we wanted to review what you gave us there for those formulas on those two again, on 5 and 6.
5 and 6. Let me take a look here. So who would have them right in their homework?
Did any of you have it right in the homework? I had it right.
I know, but I can't check your grade because
I know. What was yours right, Sean? One of them was, but the angular acceleration was not. He doesn't remember which ones were.
Let me just go and see here. 5. Okay, and 6. So looks like 5 is all.
Yeah. Okay. Jared's were right for 5 because I showed him how to do it the way I had done it. So his were right.
I can't even remember what I told you. Let's take a look at the problem again really quick.
Well, I have it written down.
Okay.
Yeah. So you gave us that. So the torque, the radius times the mass of the block times gravity equals the moment of inertia times the angular acceleration of the pulley.
Yeah.
And so that would be 1/2 mr squared, the mass of the pulley, times the radius squared, times the angular acceleration.
Okay.
Correct. So
I would assume so. Yeah. I can't really. I'm doing two things at once here.
Okay. Well, anyway, when we solved that for alpha and plugged the numbers in, it did not get the right answer for the angular acceleration.
Okay. Now I'm looking at the code. Let me see what the code is doing here. Okay, so for angular acceleration, okay, for acceleration, whoa, what are they doing here? Is this the right one? Number 10, is that right?
Number 5.
Number 5. Chapter 10.
Right.
So what was your formula for the acceleration or the angular acceleration?
My formula or what you had given us?
Your formula.
My formula I solved for the acceleration of the block, the linear acceleration.
Right.
The downward acceleration of the block being the mass of the block times the gravity, so basically the weight of the block, divided by 1/2 times the mass of the pulley plus the mass of the block.
Okay. And you got to that doing what?
Using the tension being on the cable being 1/2 the mass of the pulley times the acceleration of the block. Because your pulley, yeah, I don't even remember all of this now that I'm looking at it. The radius times the tension there would be the moment of inertia on the pulley times the angular acceleration of the pulley.
Yeah, I was thinking that both of these approaches should give the same answer, thing. But I'm not. I'd have to go through and look at the math really closely.
Okay.
But in the code, they have the same formula you do, and that's fine.
Okay.
So
we'll just go that way with it.
Yeah, I'd have to look more carefully at what I did. I can look at the video what I did yesterday, see if I made some mistake.
Okay.
Entirely possible, but
okay.
because that approach should be just fine.
Okay. Okay, and then on number 6, I don't know, did anybody have this right on number 6? Because we were having trouble with the acceleration and the angular acceleration. And so what you had shown us ended up being like 9.8 gravitation, g times the sine of the angle.
Uh-huh.
And this was the one where the sphere was rolling up the ramp.
Yeah.
And yeah, we couldn't get that. I mean, that wasn't right when we did that. 9.8 times sine of the angle.
Let me take a look here again. So the formula that I worked out was gravity times sine of the angle of the ramp. Is that correct?
Yeah, gravity times sine of the angle of the ramp. Yeah.
Let's see, what is this here? Okay, so object. I see. So in that, when we were talking about it the other day, did we never account for what kind of thing is doing the rolling? I thought we did, but if we didn't, then that would be where the mistake is, because
Yeah, that's what, no, we didn't. And that's, and I don't know if they were all, mine was a hollow sphere. I don't know that they were all that though.
no,
Yeah.
they're all different randomly.
Yeah.
And that has to be taken account for. If I didn't take it in that into account, then I didn't finish the problem.
Okay.
As we can go back and do that, we can go back and look at both of those if you want, or just 6 if you want, whatever. But that definitely has to take into account that that particular shape.
Okay. Yeah, let's look at 6. I think we'll be okay on 5. We'll just go about it doing the linear acceleration first and then solve for the angular from that.
All right. Let's see here. Let me all right. Oh, where'd my class go here? Okay, so chapter 10, right?
Yes.
Number 5, number 6.
Number 6.
So here we are. You see my screen there? Okay, so what we need to do here is, let's see, omega is easy. We figured that out, I think.
Right, yeah, we did.
We're trying to do, and once we get either the acceleration or alpha, the rest is really kind of easy. So we kind of have to decide which one we're going to go after, either alpha or A. It doesn't really matter which one you try to calculate. It's kind of up to you. But the idea of this is actually comes from the forces on whatever shape you have here, right? And so what we need to do is we need to draw a free body diagram. And on this thing, we have weight, which is pulling down straight from the middle, like that. Actually, I'm going to redraw this in a different place, a little bit bigger. Make it easier to see what we're doing here. All right, so there we go. There it is when it's at the top of this thing. We have its weight, which pulls it down kind of this way, right? And then the only other force, well, there's two other forces on this, I suppose. There's the normal force, which pushes upward on it this way. But the only other force besides these two forces is the friction. And since this thing is rolling down this way, right, the friction is pushing this way, right?
It's rolling up the ramp.
All right, rolling up the ramp. So the friction is this way. Rolling up the ramp, which means the friction is pushing that way. Okay, right. Now we're going to do everything in a coordinate system that is perpendicular and parallel to the ramp. And then we're going to get, that means that our weight is going to have two components. One that is perpendicular to the ramp right there, one that is parallel to the ramp right there. All right. And then we need to talk about what it is that is, which force here is accelerating this thing down the ramp, and which force is, or up the ramp rather. No, actually the acceleration is down the ramp because it's from gravity. So it's gravity that's accelerating it down the ramp, but it's this particular component of gravity down here that is slowing it down or accelerating it down the ramp, right? And it's the friction that is turning the object. So the friction does the turning, the gravity does the accelerating this way. Actually, it's more than just the friction now that we're looking here. We have friction, doesn't even actually tell us anything about the friction, does it?
No.
So we can't actually even mess with the friction at all. We have to just talk about gravity. I can't remember if I talked about friction last time or not, but we can't actually talk about the friction because they're not telling us anything about friction. So there's nothing to talk about with that. So we'll get rid of the friction. So there is actually gravity pulling on this at an angle from the point of rotation. Oops. And that would, so gravity is actually also giving it some angular acceleration, I suppose. Yeah. Okay. So anyway, as it's rolling along, we have two kinds of acceleration. Of course, we have the linear acceleration, which is slowing it down linear, and then we have the linearly, and then we have the angular acceleration, which is how much it's slowing down angularly. And those are happening from different forces or from different situations. The gravity, we've split into our components. We have our normal force acting on the ball as well. pushing upward to keep it from falling down this way. And so the gravity force acts right through the center of mass. So does the normal force. It acts right through the center of mass. So neither of those is going to cause a rotation around the center of mass, which is fine because we can actually consider the rotation around the edge of the ball, but only. Let's see here. I have to look at the code and see if that's what they're talking about there. It doesn't look like it. G sign. Oh, I guess it is that they're doing. Okay, that's fine. Yeah, so they are doing that. And that's fine. This is a perfectly good way to look at it. Look at this. What they're doing here. So this force, this is the gravitational force. This is the gravitational force in the parallel direction. And we can imagine this force as acting on the center of mass of the ball. So we go ahead and move that up here. So that's the force which is causing the acceleration down the hill. So we can also consider it as a force that is causing a rotation about this point on the edge of the ball. And so as we do that, then we get a linear acceleration and angular acceleration happening from the same force, essentially. So for the equation that we're going to set up, let me see if I can draw a decent equation here. We want to have force equals mass times acceleration, and torque, which is R times that same force, equals I times alpha. That's not gonna help us. Hold on a second. Having a hard time keeping track of all the stuff they've given us here and what they haven't given us. Hold on a second. They've given us the cylinder, the radius. This starts to slow down. Velocity. Did we learn I can't remember if this chapter taught us the, let me just check something here really quick. Did we learn about the parallel axis theorem? I don't remember if we did or not. I don't think we did. I think that's in the calculus-based version of this class.
Yeah, and I tried to use that about the rolling down the incline, but it just didn't work.
Well, no, because that problem there where they do this rolling down the incline is a completely different problem.
Yeah,
I'm thinking to solve this, you actually need to use the parallel axis theorem to solve it with what they've given us without having the friction. But I don't think we actually learned the parallel axis theorem. I don't remember teaching it. I'm looking to check to see if I just missed something here. Forgot to teach something, but I don't remember it being in the book.
yeah, I don't remember that either, but
No, it's not in here anywhere. Let me do one more thing. I'm going to search the book really quick. No. So, yeah, I think actually to solve this, you actually have to use the parallel axis theorem. I'd have to go and try a couple other different solutions to see if it's possible to do without it. But I don't think it is. Let me think it really quick. Let me think it through really quick. Just hold on a minute. I'm gonna talk to myself for a few minutes and see if I can find a way to solve this without the parallel axis theorem. Because it looks like in the code that they've solved it using the parallel axis theorem. But I'm not certain about that. But I just need to think about it. So hold on just a second. Put my thinking cap on here. Oh, that's not right. Summation plus. Okay, I can't see another way right away to do this without the parallel axis theorem. So I think that this problem is actually meant. I don't think it's meant for this level of this that this book teaches. I don't think I caught that before. Unless I just taught parallel axis theorem without it being in the book, which I've done that before, teaching things that aren't in the book by accident. But apparently, you don't need to know how to do that question. So I'm going to have to remove it, I suppose. I will look at it again to see if that's the case, but I won't make any of you do it. It's entirely possible that I've missed something. Usually it takes a good sitting down with a lot of paper and pencil to make sure I haven't missed something about that. But as far as I can see, it looks like it's using parallel axis theorem, which we haven't learned. So I'm going to remove that question, which was number 6.
yes.
All right. So that should not be showing in the homework anymore. I apologize for that.
No problem.
Okay, so chapter 10 homework. Any other questions from chapter 10 homework? Are we pretty good to go for the rest of that?
I think we're good on the rest of them.
Okay. So let's go back in time and look at chapters 6 through 9. Anybody have particular questions about those chapters?
I have the number 2 from chapter 7.
Chapter 7 homework number 2. Oh, yes. This is a favorite of everybody's, right? So one of the things that is most often, this problem freaks a lot of students out because it's on an incline. You know, you've got all these different things you got to answer, but remember that work is much simpler than it seems. So while there is some math to do here, it's not maybe as difficult as it might seem. So remember that work equals the force times the force that's doing the work times the distance the object moves times the cosine of the angle between the work and the distance vectors. Right? So it's important to define the force that's doing the work, to define the distance that it moves, and the angle between those two. Now, it's also sometimes important to just define the force in the direction that it moves, and that's what we're going to do here because it's actually it's a bit easier that way. And so, but also, I mean, the thing that really makes people crazy is this distance part. If it's not moving in the direction that the force is acting, then there is no work done in that direction. So that means immediately we know the work done by two of these forces. Which two of these forces do we know immediately the amount of work done?
Tension and friction?
Why do we know the work done by tension and friction?
Because he's moving down the hill, so he's not going back up.
Okay, so he's definitely moving down, and he's definitely moving. But remember the angle that when we talk about direction, we're talking about this angle here, and the cosine of 180 degrees. In other words, if it's opposite the direction, if it's anti-linear to it, then this just becomes negative. It just becomes negative work. It doesn't necessarily mean that there's no work done. But if it's cosine of 90 degrees, in other words, if the movement is 90 degrees to the force, then cosine of 90 is 0. And are there any forces here that are 90 degrees to the movement of the person?
The normal.
The normal force. So this one we will know right away is 0, right? I said that we knew 2, but we actually only know 1. But anyway, so this one right away, the force done by the normal force is going to be 0. Now the other ones are going to all have forces and directions that are either in the same direction or in opposite directions so that you get a negative sign. And let's see, this guy is being lowered down, so we know that he's moving this way. We'll give him a velocity of this direction. And that the force of gravity has 2 components. It has one this way and one this way. And that means the force of gravity has some force in the direction of the movement, right there. So the work done by the force of gravity is going to be the force of gravity in the direction that he's moving, which is the weight. Let me go ahead and just write that in, the weight of the object. So this is equal to the weight, m times g. And then you have this angle, which is the same as the angle down there, theta. And since this is next to that angle, it's mg cosine theta is our force. That's our force. the distance that is moved is whatever distance the person moves, which is 77 meters here. So this mg cosine theta times distance, and that should give me the work done by gravity. That's this one down here. This is the force of gravity in the direction that he's moving and the distance that he's moving, right? And since the cosine here is 0 degrees, then this is just going to become 1. So it's just mg times d. Just like that. So that's the gravity one. That one's done there. Now, how about the one from tension in the rope? What's the tension in the rope? Well, it's this one, right? The work done by the tension in the rope. Well, how much work is done by the tension in the rope? Well, the force, the sum of the forces tells us that we have one force going down the hill this way and two forces going up the hill this way. So in other words, we have tension plus friction. Can't draw very fast. Minus mg cosine theta. There we go.
Sorry, first of all, this is not the final bill. I just need to make a quick announcement of a very brief FFA meeting in the auditorium right after school for all FFA members.
So this tells us that the tension plus the friction minus this is going to equal 0 because we have no acceleration. They're a constant velocity, it says right here, so no acceleration. So these three have to add to equal 0. Well, we know this one. We know all the numbers for this one. And we can figure out the one for friction because friction, they tell us the kinetic coefficient of friction right there. So we know that the frictional force, if we calculate that over here, is equal to mu k times the normal force. Well, they told us what mu k is, whatever it is. And the normal force is equal to, the normal force is actually equal to this component of the gravity because this gravity pulls them into the snow. That one, the normal force pushes them out of the snow. And this one is opposite this side. So the normal force, you get mu k and the normal force is going to be m times g times sine of theta. So that tells us the frictional force. Now, you know the frictional force and you know mg cosine theta because you can plug all these numbers in. And if you plug them all into this equation, you can calculate the tension. And from the frictional force, from this one, you can multiply it by the distance, 77, and get the work done by friction. But remember, the friction points up and the person's moving down, so they're in opposite directions. This one's going to be a negative one. Multiply this force times this distance here. And then the work done by tension is also going to be negative, but you're going to have to plug this one and this one into this equation and solve for tension. And then go ahead and calculate the work done by tension. You're done. In the end, the bottom one will be positive, calculated directly, and the bottom top two, rather, will be negative because they're pulling in the opposite direction of movement, and those are just calculated. Can you see how to get through that, the rest of that problem?
Yeah, except are we using the 54 degrees or the other one? For
You
theta?
use whatever angle that they show you in your problem. Oh, sorry.
Okay.
Sorry, you mean oh, you mean because I placed my angle here incorrectly? Yeah, that's bad.
Yeah, I was just a little confused.
Sorry about that. I did place my angle incorrectly because I was concentrating on trying to draw with my trackpad. It drives me crazy. I need to get my mouse charged again. So you're right. It is actually this angle, which changes both of these. This one now becomes sine, and this one becomes cosine. Sorry about that. It's so hard to draw with this stupid thing. So that changes this to sine. And this one to the sine. And this one to sine. Crazy, crazy thing. I actually assumed it was sine here because I got this part right, but that's okay. No, this one is actually still root to my normal force.
Oh, yeah, I'm kind of
Which one is
confused about that.
Sorry, this one is still the same one. Sorry. This one's still cosine because that's the normal force. Sorry, go ahead.
Yeah, I'm kind of confused about that part of it, the
This part
gravity.
here.
Yeah,
So the work done by the normal force, I got all that. I did that one correctly because that's a different angle. That's not talking about this angle. That's talking about a different angle. Let me show you that really quick. So this right here is just the formula for the work done, right? Instead of the forces. These ones are all the forces, and you still have to multiply these forces by distances to get work down here. This one is directly the work equation, where you take the force times the distance times the cosine of the angle between them. So this one is just the cosine between the normal force here and the distance moved, which is this way, which is 90 degrees. So this one just becomes the cosine of 90, which is 0. So does that make more sense now or no?
well then that makes that 0. So the force done by gravity would be 0.
Oh shoot, this is the one for gravity. Sorry, I thought that was the one for normal force. Now I'm not remembering what I've done here. Okay, so let's go back to this one. This one is still sine. Sorry. So this one was this guy right here, right? So this is mg sine theta. There we go. And yes, so this one is still mg sine theta, sorry. So that one is not affected. This one is the only, I need to get my mouse working and I don't have it charged, so I can't get it working. I should have gone back to my office to teach this class, but I decided to come home. I'm gonna go get a different mouse. Do I even have a different mouse? I don't think I do actually here. That's not gonna work. Okay, I'm gonna redraw all this to try to do a better job drawing. I don't know if I'll be able to, but let's see. Okay, let's try again. So now I'm going to go, so first of all, there are two different angles we need to deal with. The angle of the slope and the angle between each force and the direction it moves. So this angle here, we're gonna call theta just like they did. The angle between here and here and here and here and all these forces, that's what we need to do down here. And that's probably the thing that confuses people more than anything in this problem. Everybody who does this problem well, almost everybody who does this problem just calculates the forces and puts them in down here, which is not what we're calculating. We're calculating the work, right? And the work is not the force. First of all, work is not a vector and it has no direction, but work can be positive or negative. What makes work positive or negative? What makes work positive is if your moving vector, your displacement vector, is in the same direction as the force vector. That gives you a positive work, right? So the ones up here that will be positive will be the ones that are moving, that are pointing in the same exact direction as the object that's moving. That's the gravitational vector in this direction. That one right there, which we'll call, I hate that they call it force gravity because then I have to draw more. I'm going to call this weight. No, that's not good. That's because that's the same as work. But anyway, I'll do it. I'll just draw more. This will be force gravity parallel. And I'm going to try to draw it very carefully. So force gravity parallel is pointing this way and the displacement is this way. And so that tells us that the work done by gravity must be a positive work. So I'm going to put the positive there, and then we won't have to worry about the angle anymore. If the displacement or the movement and the force are in opposite directions, then the angle between them is 180, and the sine of the cosine of 180 rather is negative. So that will always be negative work. If the force is opposing the movement, that is always negative work. So these two, the friction and the tension, are both pointing up the slope while he's sliding down the slope. So these ones have to be negative, right? However, if your displacement and your force are perpendicular to each other, then the work is always 0, because that's a 90-degree angle and the cosine of 90 is 0. And so F times D times cosine 90 becomes 0. The work is 0. So this one is 0. Now that we've worked now we've worked out the problem with the angle between the force and the displacement here. Now the only angle we have to work with is theta, so we don't have to think about it anymore. So now I'm going to go back and rewrite these things. Which force goes with each one of these works? Each work goes with a different force. Well, this one, of course, is obvious, the force of tension. It's Ft. So this one's going to be negative Ft times the distance. The work done by friction is going to be the friction, negative F, times the distance. This one here is going to be the work done by the force of gravity. Well, the only direction where gravity, the only component of the gravity that points in the direction he's moving is this one. The other one points perpendicular to it, so it doesn't do anything in work. So we have to take FG parallel times distance for this one. That's much cleaner. Wow, my fingers hurt from doing that. So now the only real problem is we know what D is. It's 77 meters. That's the easy part. But we do have to figure out what the force tension is, the force of friction, and we have to figure out the force of gravity perpendicular, right? So how do we do those three? Well, for the this one is probably the easiest one, force of gravity parallel, because this angle right here, and if we finish this triangle, and this angle theta right here are the same angle, then we know that this is opposite the angle theta in this triangle here. And we have the force gravity as our hypotenuse, so it's force gravity times sine theta. And that was the slip up I made writing this out last time. So this force is force gravity parallel, and if we plug it in right here and multiply it by 77 meters, then that part's done. These two parts require a little bit more work, so friction is probably the next easiest one to do. The force of friction is the normal force, this force right here, times mu k, which they give us right here. Right? So force friction rather, this one, equals the normal force times mu k. Now, oops. UK we know, but do we know the normal force? Well, the only forces in this direction that is perpendicular to the slope is the normal force and the gravitational force down here, the component that's pointing perpendicular to the slope. So this right here, which we'll call FG perpendicular, has to equal that one in order for them to add to 0. It has to be equal and opposite to force normal. So that one has to, so this one has to equal this one, and it's next to the angle theta, so it ends up being, this is force gravity perpendicular, which equals the force normal. And that has to equal, because we know it's equal to force gravity times the cosine of theta. So that one can go right into here for friction. Force gravity cosine theta. Now, of course, both of these having a force gravity in them, remember that force of gravity is m times g. So this one ends up being negative m times g for force gravity times cosine theta times d. And then this one ends up being positive m times g times sine theta times d. Now for the last one is the one that you have to go back to Newton's second law and say, well, all the forces have to add together to equal 0 because this thing is not moving with any acceleration. It has a constant velocity. So all these forces in the parallel direction have to add together. And that means that our FG sine theta, which is FG parallel, which is a negative force, negative FG parallel, we're calling that one negative, or we can call it positive, doesn't matter which one we call it. But the other two have to be negative if this one's positive. Either way this works out has to equal, or sorry, plus the force of friction plus the tension. All of those have to add together to equal 0. And since we already know two of those forces, we can calculate the friction force and we can calculate FG parallel. We can plug those two forces in from here and from here and solve for the tension force. Once we know the tension force, then we can plug it in here and multiply by the distance and be done with the work force done by tension. Work done by the force of tension.
Okay, that makes sense. Our bell did ring, so.
Okay, sorry about that. All right. Yeah, so that's all recorded and I will upload those today. And tell the students that if they have any more questions, they can go ahead and send me emails and I will get the test ready for tomorrow.
Okay, sounds good. And you will have the password on that again for me to put in, is that
Yeah,
right?
I'll send that to you.
Okay. All right, sounds good.
Have a good one.
Thanks. You